Did that work?
Yes.
Good. All right. Um, so I'm a radio astronomer, and the teams that I've worked with use radio telescopes to do observations in order to try and answer this old human question about whether we're alone. And SETI, which we've used a number of times already, I think most of you know, but it's an acronym, and it stands for the Search for Extraterrestrial Intelligence. But in order to understand how difficult that search may actually be, I'd like to sort of change your perspective and have you think about here and now in the largest possible context. So we'll start with here. So what do we mean by here? Well, for many of you, it is probably like it is for me. I'm here at home, right? Working from home, Zooming from home. And that home happens to be here in the Berkeley Hills in California, right? In the San Francisco Bay Area. And if we were at the altitude of low Earth orbiting satellites, I'd see myself here on the west coast of the United States. And since 1968, when Bill Anders took this Christmas Eve photo of Earthrise, we've been able to envision ourselves here. This is our first truly cosmic perspective. We got to see our planet floating in the blackness of space, and this really became an emblem for the environmental movement. And of course, in the summer of 2013, the Cassini spacecraft, which was orbiting Saturn, looked back and saw us here, the little tiny white dot at the end of that arrow. So I hope you all got the memo and went outside in your best clothes, and waved at Cassini to participate in this selfie of Earth. Before that, in 1990, the Voyager 1 spacecraft was passing by Neptune, and it turned around and looked homeward and gave us this image of a pale blue dot caught in a ray of sunshine and dust. So we were here, the pale blue dot. And indeed, our star is one of something like 400 billion stars in a galaxy that we call the Milky Way. Now, I've been showing you actual photographs until now. Yeah. This is not a photograph of the Milky Way because we can't get outside of it to look back and take such a photograph. But it is a photograph of a galaxy called M101. We think that that's what our Milky Way looks like if we could get outside and look back. Now, we can't do that in the optical. We can't take a picture of our galaxy in the optical, but at radio wavelengths, we can study the carbon monoxide and methanol gas and dust in the galaxy, and we can actually map the galaxy from the inside out. And we just concluded that project, which took something like 15,000 hours of telescope time to do it. And this is our best map of what we think our galaxy looks like. And if you compare it, right, I think that we're on the right track. So the other thing to realize is that although there are 300 billion stars in this galaxy, there are a comparable number of galaxies in the observable universe, each one of which has a few 100 billion stars. And so this is a beautiful photo taken by the Hubble Space Telescope. And you'll notice that each of those points is a whole galaxy. It isn't a star, it's a whole galaxy with hundreds of billions of stars. And some of the points are smaller and fainter. And that's because they are farther away. And now we remember that because of the finite speed at which light travels, that as we look farther away, we're also looking further back in time, because it's taken the light longer to get here. And so this is what we have as a context for here. And as a context for now, we have to think about the fact that we are at this moment, after something like 13.8 billion years of evolution of our cosmos. And we have this pretty artist concept, and there are lots of things that astronomers have studied in this expanding and evolving universe. But we have to admit that we've actually observed only about 4% of the total matter and energy density of the cosmos. So the physics that we know, or we think we know now, is consistent all the way back to the earliest times, smallest sizes and heaviest or greatest densities. And when you get back to that very early instance, we have to admit that we can't make gravity and quantum mechanics play nice together. So this is the most self-consistent picture of cosmic evolution that we can show you, but we're pretty sure it will change, maybe only in fine details as we learn more and go forward. So I've told you about faraway places and long ago times. And it's important to think about those because we humans are actually intimately related to those places and times. We humans chase our lineage not just back through the centuries of our families, not just back through the millennia of our architecture and art and all of our different experiments with governance. We trace our lineage not just back over the millions of years since we've branched off from the apes, and not just back through the 2.4 billion years during which the Earth's atmosphere has been perfused by oxygen due to the photosynthetic labors of blue-green algae, cyanobacteria. And not just back to the 4.568 billion years ago when our solar system, our sun and our solar system formed. But we need to go back a few million years before that to a large molecular cloud of gas and dust that was contaminated by the winds of Wolf-Rayet stars and the debris of supernova explosions. What I'm showing you here is a modern supernova explosion. But we go back billions of years to a molecular cloud that had the debris from such an explosion contained within it. And the iron atoms in the hemoglobin molecules of your blood and the calcium in your bones and all the other elements that are heavier than helium that make you who you are, they were all fused up in the heart of massive stars that exploded, and the debris was captured in a molecular cloud that then condensed to form the solar system. But that's what you're made of. That is literally the stardust that you're made of. And so what we can say is that it actually takes a cosmos to make a human. And it's taken us about a millennia going down this road, this journey to try and understand who we are and where we came from. And we're driven on to continue the journey because of curiosity. And we want to know what else might be out there. And of course, who else might be out there. So over my career, there have been two spectacular game changers in the 20th century. First is extremophiles, and the second is exoplanets and perhaps exomoons. So extremophiles are forms of life that we didn't know about until a few decades ago. living in environments which, when I was a student, I was told could not possibly support life. And yet it's there and thriving. And we're just beginning to learn the different ways that life can figure out how to make a living. And that is illuminating lots of new possibilities, perhaps, for life on real estate beyond the Earth. And the other thing that we now know, which we didn't know when we got started with this SETI enterprise, is that there are more planets than stars in the Milky Way galaxy. So altogether, we now know that there's potentially a lot of habitable real estate out there. And the next question is to ask whether any of it is actually inhabited. And so within the discipline that we call astrobiology, we have a large number of scientists who are thinking about looking for biosignatures, basically thinking about life potentially on other planets and moons in this solar system, which we have an opportunity to investigate with spacecraft and robots, and thinking about looking at the atmospheres of distant exoplanets orbiting other stars. Right? When we look at the Earth's atmosphere and we compare it to the atmosphere of the other planets, particularly here we show Venus and Mars, we see that the chemistry of our atmosphere is greatly out of equilibrium. We have in the atmosphere at the same time molecular oxygen and methane gas. And those two gases are very reactive. If you put them together in the laboratory, you're going to instantly have carbon dioxide and water. And that's going on in the atmosphere all the time. But because we have a biological source function on the surface of the planet that is constantly replenishing these gases, we have oxygen from photosynthesis, and we have methane from bovine flatulence, cow fart. Right? That's really marking our atmosphere as a disequilibrium state. And we wonder if we can detect these same sort of biosignatures in the atmospheres of distant exoplanets. Very, very hard experiment to do. First of all, the signals are always going to be faint, and the signals are coming from a planet that is right next to a big bright star that we can't separate the light from the planet from the light from the star. So we have to use other techniques to actually try and do this. And we've had some minor success with a couple of very giant hot exoplanets that are far from their parent stars. But it's really a difficult job, and it's fraught with ambiguity. You know, is there something else that can produce oxygen and methane? For example, a couple of months ago, there was a claim that phosphine had been found in the atmosphere of Venus, in the clouds of Venus. And the reason that that was interesting is because we can't figure out any chemical network that would allow as much phosphine as was claimed to be produced in the Venusian clouds without some biological help. On our planet, we get phosphine, and it's a product of biological activity. And so there are a lot of question marks on that slide. First of all, it was single line detection, and so did we actually get the right molecule? And secondly, is there any chemical network that we just haven't explored and thought of that will produce the phosphine in this abundance? So even very much closer to home than a distant exoplanet, this question of finding biosignatures is fraught with ambiguity. There are indeed false positives. So what about finding technology? Well, we talk about looking for technosignatures. These are likely to be less ambiguous. And also probably more difficult to find. So we think about our technology, and our technology today is visible at the distance of exoplanets, and maybe theirs would be too. We actually don't know what technologies they might have invented, what the technologies they might be using, or for what purposes. So we have this difficult question of how do you build a detector for something that you don't know about? And the answer is the only thing you can do is use us as an analog and use the technologies that we have available to us today. So SETI researchers looking for technosignatures are using the tools of the astronomers, and they are building some of their own new tools. So this journey to look for technosignatures began in 1959. There was a paper in 1960, the first search at radio. And then later on, we added optical searches. And now we're pushing into the infrared. So we're trying to cover as much of the electromagnetic signal spectrum as we can. And what we're looking for is engineered signals, something that doesn't look like what Mother Nature produces. And here's a slide where instantly you can see that there's something going on here. There's a lot of noise, but there's something that isn't noise. And in this case, it happens to be a couple of spacecraft orbiting Mars. So this is a what we call a waterfall plot. Time increases vertically and frequency increases to the right. And each of those dots is an observation. How much voltage as a function of time did we detect at a particular frequency when we made the observation? And most of the time, what we see is just that noise. And sometimes we see engineered signals, such as these, and it turns out to be our own engineered signals, terrestrial engineering, satellites, radio broadcast, television broadcast. So we do have this problem of false positives, but it is a bit easier to disambiguate it. It is easier often to distinguish between an engineered signal coming from Earth and an engineered signal coming from the sky, and not an astrophysical one. And one of the things that we do is we observe with multiple telescopes at the same time, looking at the same place in the same way. And if you see the same signal in both telescopes, then you know that it's not likely to be local interference or an instrumental problem. It's much more likely to be the kind of thing that you're actually looking for. So in order for SETI to succeed, technological civilizations are going to have to be close to one another, right? And that means not only close in space so that the signals are strong enough so that our detectors can find them, but close in time, overlapping in time. So we live in a galaxy that's 10 billion years old. In order for two technological civilizations to be cotemporal, to overlap in time, they have to be long-lived. And that's actually the reason that I enjoy working on SETI. So Philip Morrison called this concept, he is an early pioneer in SETI, he called the concept the archaeology of the future. Any signal that we find out there and any information that it might contain is archaeology because of the finite speed of light. It's taken the signal a long time to get here. So we're learning about their past. But the fact that we detect a signal, that we succeed, means that we can have a long future. Technologies on average apparently then are long-lived, and somebody else made it through this technological adolescence that we find ourselves in. And so if someone else made it through, we can as well. And this, I think, is the real benefit of SETI research and looking for somebody else's technosignatures. Now, I mentioned that the first paper was in 1959 and the first search in 1960. Well, how much searching have we done? If you take all of the different directions in space and all the different frequencies and polarizations and modulations and power levels that we might have to search through to find a signal in the electromagnetic spectrum, assuming that that's what we should be looking for, that's a 9-dimensional volume. And I just said, okay, I'm going to set that volume equal to all the world, all of the world's oceans combined. And then I calculated that in 50 years, we had searched one 12-ounce glass out of the oceans. And now 10 years later, Penn State students just redid that calculation and they say it's more like a small swimming pool or hot tub, right? So our searches are getting bigger quickly, but there's certainly a very long way to go. And people sometimes talk about something called the Fermi paradox. They say, where is everyone? Or Fermi was supposed to have said at lunch in Los Alamos once, where is everyone? And the argument goes that it's been such a short time since we developed technology and we're on the verge of space travel that any other technology out there that ever existed would surely have become spacefaring, and it doesn't really matter on how you model the travel, they would have by now colonized the entire galaxy, but they're not here. So there can never have been another technology anywhere or anywhen. We're the first. And I don't buy that. I don't think there's any paradox. We have so poorly explored even our own back step, our solar system, much less the cosmos, that we shouldn't be surprised that we haven't found any evidence yet. We just have hardly begun to search. So there's no paradox in my world, anyway. So we've begun to build some of our own tools. We've used a lot of the astronomers' tools, but we're now building our own. And this is the Allen Telescope Array in Northern California. It's the first time that we've built a telescope, a big telescope, out of a large number of small dishes. And it's the first time that we could, because it takes a great deal of computing to essentially make these many small dishes into one large dish. And so in our world, silicon is as important as steel and aluminum. And these telescopes are working at the Allen Telescope Array every day, looking for SETI signals. Actually, right now, we're refurbishing, putting in better receivers. So they're not working right today, but they've been working since 2007. The other big SETI project that has started recently is called Breakthrough Listen, and it's been funded by a $100 million 10-year grant from Yuri Milner. And they want to look at all 43 stars within 5 parsecs. Parsecs about 3 light years, so that's within 15 light years. And a light year is the distance that light travels in 1 year, about 6 trillion miles. So 43 stars within 15 light years, 1,000 stars of all spectral types out to 50 parsecs or 150 light years. They want to look at 1 million nearby stars. They want to look at the central regions of at least 100 nearby galaxies, and then various exotic objects. So this is their observational plan for a decade, and they are observing away. They have built very beautiful computing backends and receivers for the Green Bank telescope in West Virginia, 100-meter telescope, for the Parkes telescope in New South Wales and Australia. And some of you may have noticed that Parkes was recently in the news because of a signal that someone thought they had found in those observations, and it got leaked to the Guardian newspaper, who went kind of wild about it. And nobody is willing to say that this is an extraterrestrial signal from another technology. It is almost certainly from our own technology, radio frequency interference. But we can't, because they're only using a single telescope. They don't have a second telescope, which would validate and confirm that detection. It's really hard to say what that was. The reason that they don't think that it's a signal coming from the direction on the sky they were pointing at from a long distance is this. All right, this is another one of those waterfall plots. Frequency increases horizontally towards the top. I'm sorry, time increases horizontally towards the, let me get this right. Time increases vertically up towards the top, and frequency increases from left to right. And there's a signal there, and I've let you stare at it for a while, and maybe your eye has picked it up, but our computers have no trouble picking it up. That's actually a signal from the Voyager 1 spacecraft when it was 106 times further from the Earth than the Earth is from the sun. And the transmitter on board that spacecraft is 30 watts, about a third of your usual 100-watt light bulb. That's all the power it was. And here's the signal, and now you can't unsee it. And this is what it looks like to our computer algorithms. But you notice that at the earliest times, down at the bottom of the picture, the signal starts at one frequency. And then over time, going towards the top, the signal drifts to lower frequencies. And that's because the Earth is spinning. That's what gives you that Doppler shift. Well, so over time, signals coming from the sky shift to lower frequencies because of the Earth's spin. Well, the signal detected by the Breakthrough Listen team shifts the other way. Doesn't look like it is a Doppler shift due to the spin of the Earth. Now, it might be a clue that indeed this is somebody else's technological signal because it's shifting the wrong way. And you can do that in the laboratory. You could make a transmitter that would give you a signal like this. So, I mean, it's a question, and I don't think that we'll ever know what that signal actually is. And it's why, I'm on their advisory board, and I'm always beating the table and saying you need more than one telescope to believe a transient signal, because every time they've looked back at the same position on the sky many times and haven't actually seen this signal again. So it's a mystery, and I think it will remain one. Right? It's not just radio. We've been doing optical SETI, and here's the automated planet finder telescope at Lick Observatory, which Breakthrough Listen will use to search for signals, and now has detectors on. And there are other telescopes with which Breakthrough Listen has memorandum of agreement and are beginning to build back-end detectors for. You can see the large telescope in China called FAST. In the middle is an array in South Africa, where again, it's now an array of small dishes. And then on the right is Jodrell Bank and the Merlin array. And Breakthrough will be working with all of these telescopes in the future. And there's more SETI. Until December, we had a nice program going at Arecibo, the Berkeley group did, with SETI at home and piggybacking on the radio data that Arecibo was collecting. But sadly, that telescope collapsed in December, and we've lost that very large year on the universe. There's low frequency arrays across Europe and the Netherlands. There's an Italian program using a 64-meter dish at Medicina. Down in Southern California, there's a Goldstone Apple Valley Radio Telescope and a program being run by students, which is doing a sky survey. So instead of pointing at specific stars, it's rastering the sky, moving the telescope back and forth to cover all of the sky. And there's another low frequency array in Western Australia this time, called the Malera Wide Field Array, which is also beginning to do SETI. In the optical, we've looked at the sky that's visible from Harvard University now about 8 times after the students built their own telescope and detectors. And we are reanalyzing all of the data taken by the Keck observatories in Hawaii. And these data were taken to study stars to see whether they have exoplanets around them by looking at how the planets might tug the star forward towards us and away from us. And those data are all being reanalyzed to look for laser flashes. There's even an amateur optical SETI observatory in Bogota. And here, as I mentioned earlier, working in to push SETI into the infrared at Lick Observatory. And we can also just do archival searches. We can take a look at data that was collected for other reasons. So the WISE spacecraft made an X-ray map of the whole sky. I'm sorry, I said X-ray, infrared map of the whole sky. And those data have been analyzed looking for Dyson spheres or megastructures that a technological civilization may have erected around its star to collect all of the energy that the star can provide. And the star wouldn't necessarily be visible then, but what would happen is the backside of that Dyson sphere would be warm and would emit infrared. So the GHAT project has looked for Dyson spheres and galaxies that had been transformed into energy sources and looking for these infrared excesses. Right now, there's a telescope called Veritas. It's 4 Cherenkov counting telescopes. We didn't have to build any new equipment there. We just had to write new software. So normally these telescopes are looking for great, huge air showers coming across the sky, and they have photodiode arrays at their focus with 900 or so photodiodes, and they're looking for many of those photodiodes to light up in an air shower. Well, we just said, okay, now how about you look for the single pixel events, 1 photodiode lighting up at each telescope, but it's the same position on the sky for each of those 4 telescopes. So we wrote some new software, and that's beginning to do SETI observations. There's a program in Southern California being run by Shelley Wright at UCSD called PanoSETI. And Shelley's idea is that you build a geodesic dome, and each of the elements of that dome is a Fresnel lens, a big plastic Fresnel lens. And these lenses can focus a large area of the sky onto a small silicon photodetector. So Shelley reckons that with something like 125 or 26 of these Fresnel lenses in a dome, you can look at 10,000 square degrees of the sky. And why would you want to do that? This is the kind of telescope that you need to find optical transients. You have to be looking at all the sky all the time in order to be sensitive to these transients. And not only do you have to build one of these domes, you have to build a second one, again, for validation and confirmation of a transient event. So the next program that is again also trying to look at all the sky all the time at optical wavelengths is called Laser SETI, and that's being done at the SETI Institute by Elliot Gillam. And with 8 cameras and gratings to give you spectroscopy, it's called slitless spectroscopy and fast readout, and about 12 sites around the planet, you can actually look at all the sky all the time. And the first partial observatory is in Northern California in Sonoma at the Ferguson Observatory. That's up there on the roof. And the second set of detectors, cameras, will go to Haleakala in Hawaii once we figure out how to travel again safely and can go to install these. In the future, the astronomical community will be launching large telescopes in space that may actually have the capacity to do this imaging of exoplanets and chemical assays of their atmospheres to look for this chemical disequilibrium biosignature. The first of those we hope will launch next fall, the James Webb Space Telescope. It's hugely behind its schedule and over budget because it's new technology and it's really hard to do new things. There are some other ideas, the Roman telescope flying in precision with a star shade out in front of it to block the light of the star and allow the telescope to see the faint emissions from a planet near the star. And that will detect planets. It may, for just a handful of very nearby stars, allow us to do some biosignature detection. But if you want to do a systematic search of a lot of stars, you need a much bigger telescope. And NASA has plans, 2 plans, for building such large space telescopes that could be as big in diameter as 16 meters. And one version is called HABEX, the other is called LUVOIR. We're going through an assessment, what we call a decadal review in the astronomy community, and we'll see what the community, how they prioritize these 2 ideas. But that's the kind of thing you need to be talking about life. That's how big telescopes need to be in space. On the ground, if you had appetite for just a single purpose telescope, not a general purpose telescope, as most telescopes are, this telescope, which looks more like a Ferris wheel or a radio interferometer, it's called the ExoLife Finder. It can look at the Proxima Centauri system and only the Proxima Centauri system. And if you looked and stared at that system and you looked at the exoplanets and you looked at the intensity that you get from the exoplanet emission over hundreds and hundreds of orbits, you can indeed take and disambiguate that and make an opacity map of the planet's surface and do a search for biosignatures there. But again, astronomers don't in general have an appetite for just a one-purpose telescope. They prefer to build things that can do something for everyone. We don't know what the fate of this really ingenious telescope might be, but it should be cheap, relatively speaking, $5 to $10 million and take 5 years to build on the ground. All right, more on the ground astronomical telescopes in the optical for the future. The 30-meter telescope, the giant Magellan telescope. and the European extremely large telescope at 40 meters, which is actually downscaled from what was called the 100-meter overwhelmingly large telescope. Now we have the extremely large telescope, and the Large Synoptic Survey Telescope, which hopefully is going to come online this year and give us a snapshot of the sky every couple of days so that we can find things that change in time. And then for optical SETI, well, we talked about PanoSETI and laser SETI. And then in the radio, the new instrumentation that's being prepared for the FAST telescope in China, the Meerkat array in South Africa, which hopefully within a decade or so will grow into the Square Kilometer array in the desert of South Africa. And maybe in this country, depending on the decadal review, the next generation very large array across the southwest deserts of this country, large number of small dishes. And then if the ExoLife Finder telescope could ever be made to work, then you could grow it to something called Colossus, which is 80 meters across. And the claim is that this telescope would be sensitive enough to find the heat sources from cities on planets around a couple of dozen stars nearby. So that's what the astronomy community is looking forward to in the future. And the SETI community is wondering, what kind of back ends? How can we piggyback? How can we use these data to look for technosignatures while other people are looking for biosignatures? And so my main message is that I think SETI is really worthwhile, because if you talk to a group of people, such as I'm talking to you, I'm forcing you to think in different ways than you normally do. I think SETI has the effect of holding up a mirror to everybody on this planet and saying, see, look, in that mirror, you're all the same when compared to something that may have originated and evolved on a planet around another star. You're all the same when compared to them. And so it has the effect of trivializing the differences among humans that we fight over today, that we are so fraught by today. And I think this is an incredibly good thing, because we are facing on this planet all kinds of challenges in the near future, challenges that don't respect national boundaries, challenges that are going to have to be solved globally. So I think anything that makes us think about ourselves being Earthlings rather than being Americans and Europeans, and we're all Earthlings. And that cosmic perspective, I think, is going to be very hopeful and helpful for solving the global challenges that we face. And so the last words today are from Caleb Scharf. He's the chairman of the astrobiology department at Columbia. And Caleb reminds us that on a finite world, a cosmic perspective isn't a luxury, it's a necessity. And so with that, I'd like to give you a homework assignment, which is when you next pick up all of these electronic devices that we have, and they all have profiles about who we are, change your profile so that the first thing that you say about yourself is that you're an Earthling. And then try and act like that. Thank you.
Thank you, Jill. We've got a few questions, and people are welcome to add some more, and now is the time to do that. And please keep yourself muted unless you're invited otherwise. First question, with the search for biosignatures, differentials between the, would search for biosignatures search for differentials between the planet and its atmosphere?
I don't think that we have that kind of resolution, right? We're just going to get the full integrated light from a disk. And so it won't distinguish between the planetary surface and the atmosphere, with the potential exception of that exolife finder, that opacity map.
Would love to hear thoughts and perspective on recent RF detected by Juno at Ganymede. Perhaps also the viability and prospects of Jupiter's large moon to sustain life in some form, with calculations indicating internal oceans of water, magnetosphere, visible electric auroras, plus. Thank you.
Yes, well, we're going to go there. Juno mission is going to go there. And so both Europa and Enceladus appear to be ice-covered moons with salty liquid oceans underneath the ice. And there are things that are called cryovolcanoes, where that ocean is being explosively pushed off of the moon. And so we'd like to do a fly-through of that, and Cassini did, but didn't really have the right apparatus. We'd like to collect samples of those oceans and see if there's something equivalent to the kind of life that lives around black smokers at the bottom of our oceans. Look for organic chemistry. And so that's another mission that's under planning. There were lots of parts to that question. Did I get them all?
You can unmute yourself if you need to.
Well, that was fantastic, Ms. Tartar. Thank you so much. Just generally, the prospect of Ganymede, is that a suspect planet or a satellite, given a number of its unique traits?
Yes, yes, but Europa and Enceladus seem to have, they're a bit ahead in that race, but Ganymede is also another potential.
Is the telescope used in the Mars project doing any SETI work?
Telescope used in the Mars project. Can you be more specific? I'm not catching what you're asking.
Again, you may unmute yourself.
Yes, hello, can you hear me?
Yes.
Yeah, no, I know an astrophysicist who has been working in Colorado on the Mars project on the telescope, and I don't really know much more about it than that. I was just curious if government money that is going into space projects is also interested in these, investigations.
I'm not aware of any modifications to NASA Mars project that has been proposed that would allow us to get the kind of data that we would prefer to get. But I'm sure those data that are collected will go into public archives, and we can do this kind of archival searching.
I might know the answer to this question, but what is your opinion of Stephen Hawking's thought that searching for extraterrestrial life might not be such a good idea?
Well, yeah, Stevens and some other people as well are worried that, we maybe don't want to make our presence known because they'll come and eat us for breakfast, or basically if we make ourselves known to an extraterrestrial technology that has the technology to come here, then they're more advanced than we are, and they'll write the rule book, right? And Stephen's worried about that. He says it didn't work out so well for the natives when Columbus showed up in the New World. I'm less worried because I think, all right, now there are a number of steps in this. So we're postulating they have the technology to get here and potentially pose a threat. Well, that means that they're older than we are. And I don't know how you can get to be an old technological civilization and sustain yourself unless you outgrow the aggression that probably helped you to get intelligent as part of your evolutionary process. So I'm more in the Steven Pinker school of kinder and gentler. We are now kinder and gentler due to cultural evolution than we ever have been in history. So I think an old sustainable technology that can get here is not something that we have to worry about in terms of their deliberate intentions to act badly. It might not turn out well because of confusion, inability to communicate, inability to appreciate how you operate under the golden rule when you don't know how they might like to be treated, and they might be so very different than we are that it's hard to take our ethics and how we would like to be treated and apply it to something else that's totally different. So I think there's a problem for miscommunication. I think there's less reason to think that they are going to come and deliberately try and do us evil.
Can you say again, what is an optical transient?
An optical transient would be something that goes flash on the sky and then doesn't repeat, right? Something that happens and is a very short duration. So up until now, in all seriousness, we really haven't had any kind of sensitivity at the radio or the optical to transient signals. And but now we are trying to build systems that can look at all the sky all the time, so that when something goes off over there, we're not looking in the opposite direction, right? We want to look in all directions and find these short-lived phenomena. And in the radio, we have a lot of reason to do that, because of the last decade, we've discovered something called fast radio bursts. They only last for a millisecond. They're incredibly energetic. They come from outside of our galaxy, and there may be 10,000 of them going off every single day. And we have a hard time finding them because we can't look at all the sky all the time. So we're looking that way, right? When we need to be looking some other way.
Using the frequency drift associated with Earth rotation to identify extrasolar signal is a cool idea, but that is not a hard constraint, right? A signal source might be sitting on a planet that rotates as well. Is there some other logic one can apply to allow for that?
Yes. You can, so you can decide what angle you're going to allow that line that I showed you to appear at. If there were no drift, if in fact, one of the criteria we use, if it's straight up and down, if it doesn't change its frequency with time, then it's tied to the Earth. You know, you've got some kind of frequency standards that are in common. But the range of angles that you allow it to drift is one of the criteria that you set, and it's set pragmatically by how much computing we can afford to do. And in particular, in the projects that I worked on, where we did our signal processing in near real time rather than recording the data and looking at it later, that was a really stringent constraint, because there was only so much computing we could get done in the time that we had available. So we threw out signals that didn't drift, and we limited the range of drifts to be negative, and as that line could be as steep as 45 degrees. But it doesn't mean that it couldn't in nature or reality be some other larger drift. And we just used Jupiter with an 8-hour day as a model for what our most extreme drift would be. And now there are papers that are being written that consider exactly what you're talking about, and as opposed to looking at a drift that was within, that changed, the frequency changed by 1 hertz in a second. Now there are papers that say, well, engineering could in fact give you plus or minus 8 hertz per second. So we really should have been looking at more, but we're limited to the computing we had at the time. And it'll get better. I mean, that's the nice thing about an exponential growth, is it's always going to get better. And all the good stuff happens in the last factor of 2.
What is our best proof? What is our best proof or evidence to date that SETI, these questions just keeps moving. What is our best proof or evidence to date that SETI has discovered?
Zero. I would claim that there are no credible detections of extraterrestrial technology. Right? There might be a detection of extraterrestrial biology if the phosphine story in the clouds of Venus continues to hold, and that there's no way to produce that much phosphine without biology mediating the reactions.
We have a couple of fun questions.
Oh, good.
Well, I interpret them as fun. Based on all the data you have personally seen, do you think there is a possibility that alien life is avoiding detection until we are ready as a species?
There are lots of people who have written about this topic. It's sometimes called the zoo hypothesis, that they're there and studying us, but keeping themselves out of sight until we grow up enough or pass some criteria of worth. And I can't argue against that.
A similar but very different question. Do you have confidence we would be evolved enough to be ready to be gracious hosts to our cosmic friends?
That's a challenge. That's why I give so many talks. That's why I like to get this idea in front of as many groups as I can around the world. No, I mean, there are a lot of, when we look to the future, there are certainly a lot of things that indicate to us that our future might be very short rather than long. So I don't think that we're any better than adolescents. And, you know all the trouble that adolescents can get into.
Any comment on the UAP, unidentified aerial phenomena, disclosure requirement added to the COVID relief bill? Gives DoD and other US departments 180 days to release all files on aerial threats to include UFOs. CIA has already released thousands of new files in the last week.
Yeah. As I've said, I don't think there's any credible evidence of someone else's technology. Having said that, I don't see any reason not to release those files unless there's really some national security issues. And yeah, more qualified people with better equipment than I have looked at that TikTok footage and don't conclude that it's someone else's technology. But yeah, let's see what's in the files. That's why we have Freedom of Information Acts.
Would you be willing to comment on the work of NASA scientist Norman Berggren's Ringmakers of Saturn?
I have colleagues who work on the rings of Saturn and how they're changing and evolving over time. And I think it's a nice science fiction idea, but there's nothing in the data that they've been able to study that would indicate that there's a ring maker.
Can you contract with 2 telescopes for a session to get the proof, quote unquote, the proof?
Yeah, yes. We always, in the projects that I ran, we always used 2 telescopes simultaneously and separated by a few hundred kilometers at least. And yes, you can track them. It limits exactly how low to the east and west you can go at one site because both have to be able to see it, but it's perfectly possible.
Anyone else have any other questions? If someone wants to unmute themselves and ask a question, I think we're in good order here, so you could do that or put it in the comment box. Last call for questions. Yeah, go ahead, Bob. You want to unmute yourself.
What do you think of the wow signal? I apologize if it's been covered already. I just rejoined.
Well, again, if I had been running that program, you would never have heard of the wow signal, because they had a protocol built in to try and distinguish between terrestrial technology and something that's coming from the sky and moving at the rate that stars appear to move. They had two receiving systems, an east and a west, and something that was moving at sidereal rate on the sky would show up in the east receiver, go away, and then show up in the west receiver. Well, the wow signal only showed up in one of the receivers, and they don't know which one. And so it failed that verification test that was built in. And so, as I said, I would never have credited that because it failed the test. Now, the test may be overly stringent, but if you're doing a scientific exploration, you need to set the rules and keep to them. So hundreds of hours of telescope time have been spent re-looking at those frequencies at the two potential directions that the signal may have come from, and it's never repeated. So I have no idea what it was.
Dr. Tartar, thank you for your lecture. What do you think about the idea that there was life on Mars sometime in the past? You know, million years, billion years. Didn't they find something?
I think that it's possible. I think that it's possible. Life could have gotten started, you know, early on. Mars was much wetter and warmer, right? And life could have started there about the same time it did here. Or in fact, life could have started here, and because of a collision with a rock from space, it could have been kicked off the Earth, hiding inside a rock, and deposited on Mars and seeded life on Mars. Energetically, it's more likely the other way around. So we might end up asking the question, are we Martians, right? Did we start with life on Mars and then get transported to the Earth? And now that we know that there's liquid salty water on the surface of Mars, at least seasonally, it's making our observations much more difficult, because normally we say the microbes that are carried on a spacecraft that lands on Mars are not going to be able to survive. But if there are these wet areas, recurrent slope lineae, something like that, those are areas we would like to study. But if we're going to go there, then there's more of a chance that microbes that we introduce might in fact be able to survive. So this whole question of how we sterilize spacecraft is now being revisited. There's a bit of dissension in the community, and a worry that now that such explorations may no longer be the purview of just space agencies, but may become philanthropically funded and become, entrepreneurial. We have not really gotten a handle on what requirements anyone could make and enforce on those spacecraft.
What part does astrochemistry play in SETI?
Astrochemistry is a little bit more relevant to looking for biosignatures and what you might expect in the atmosphere of a planet around different types of stars. And there's an enormous amount of work going on there, building up this huge matrix of all possible small molecules that you think might be built with astrochemistry in the atmospheres of distant planets. As far as SETI is concerned, since it's the technology that we go looking for, I really don't care what made it, right? It could be little green men or big blue ladies or something else, some kind of colonial organism that can create large-scale technologies. So we're going looking for the technosignatures. If we find them, we're going to presume that at some point in time, there had to be some sort of intelligent technologists that created it. But we don't try and be we don't try and pre-filter what that biology or what those technologists might have been like or might be like.
Jill,
Yes.
you showed it had to be 30 or 40 different systems, telescope systems, and they all seem to be independently funded by different countries or different entrepreneurs. Has there been any effort to coordinate these 30 or 40, I guess, I don't know if that's the right number, to coordinate that effort? Or they all have their own ideas, so they go off in that direction?
Well, particularly, there are a couple of answers to this question. Particularly in the radio, there is an open skies policy, which means that telescopes that are funded by national entities are still open to proposals from any astronomer anywhere with a good idea. And those proposals get reviewed by some kind of time allocation committee. So in that sense, there is some international coordination. But the other thing is that square kilometer array that I mentioned that hopefully might be built in a decade or two, that's been international since the beginning, right? So we scientists came together and decided how you might build such a thing, and then a corporation then the funding agencies from the national entities got involved and had to incorporate and all of that. But that's international from the beginning, and time will probably be allocated on the basis of what fraction of the funding each nation provided.
Thank you.
We have a few more questions, but I don't know how long you want to keep going or if you want to keep going.
I think I'm about ready to run out of steam, but we can probably do one more question.
Well, the most important question, at what age did you begin your study of the skies?
My dad was an outdoor person, right? And he had an opportunity to study astronomy as a graduate student after he finished university. Instead, he went and played professional football in 1923. But he loved the sky. And so I remember being 8 years old and visiting my aunt and uncle, who were literally beachcombers in the Keys of Western Florida, and walking along on Minnesota Key, walking along the Gulf with my dad and looking up at the sky and simply thinking that, there's probably a small creature walking along the edge of an ocean on a planet around one of those stars, and it will see our sun as a star in its sky. So I've had that worldview for a long time. In the end, I got an engineering undergraduate degree and an astrophysics degree, and fell into SETI by accident because I knew how to program a PDP-8S computer that was given as a piece of surplus hardware to Stu Boyer at UC Berkeley, who had an idea to piggyback on Berkeley's radio telescope and do SETI, make copies of the data and do SETI on it while the astronomers were doing other work. And I just happened to know how to program the ancient computer that he was given. So it was an accident, and I've been very fortunate for that ever since.
Well, thank you so much for your time. It's been a wonderful presentation. Sorry we didn't get to every single question, but I think we covered a lot of them. And thank you all for coming. Thank you, Dr. Tartar. It's been a pleasure.
It's been my pleasure. Thanks for asking me. Have a good evening.
And you too. Thank you.
Thank you very much.